This paper is entitled Value Iteration Using Universal Graphs and the Complexity of Mean Payoff Games. As you can see, it is in two parts. First part is about value iteration and universal graphs, and the second part is about applying it to mean payoff games to obtain new results about the complexity of such games. This paper is from Nathaniel Fijalkow at L'Abri, Bordeaux, Paweł Gawryszowski at Wrocław in Poland, and myself, Pierre Roman, at IRIF, and is presented obviously at MFCS 2020.
So let me start by defining two-player games on graphs, which will be the object of our work. So these are given by a graph with two different types of vertices. I'm going to write squares and circles, right? So you have some squares and some circles. Okay, and then you have some edges. So I'm just writing some random game here. Now the edges are labeled by some colors. So I'm gonna use C1, C2, this is C1 again, and so on. So these are colors, okay? They belong to some given finite set C, okay? And also I should specify a winning condition, W. So W is a subset of C to the omega, so infinite words over C, right? Now, how do these work? Well, assume that we have a token which is initially placed on some given vertex, and then there's two players, right? So there's the square, so let's say that square is player 1, and there's circle who's player 2. So you have these two players, and whenever the token is placed on a square, then player 1 chooses a successor, and whenever the token is placed on a circle, then player 2 should choose a successor. And then this interaction produces an infinite path on the graph, and this infinite path sees some colors, right? So C1, C2, and so on. Now this infinite path produces an infinite world of colors. So let's call this pi. So that's called a play. So play pi is an infinite world of colors, and we say that the play is winning. So for player 1, if and only if pi belongs to our fixed winning condition W. Okay. So this is how we define a game. Okay, now let's just do some examples of games. So the first, maybe one of the most simple game would be safety games. So these are played with only two colors. So let's just call them top and bottom. Okay, and the winning condition would be just one word. So it's singleton top to the omega. So this means the square player wins if and only if he can ensure to visit only some tops. Okay. So this is what we call the safety condition. There's two colors and you should only see one color. So that's a safety game. Okay, now another example which is very important and important for us is that of parity games. So these are played with edges that are labeled by integers. So let's say from 1 to D. And then the winning condition is, so let me just write it first. So the set of plays such that the lim sup of pi is even. So this means, so lim sup is the maximal color. So in this setting we call them priorities. So the maximal priority which appears infinitely often in the play. Okay. So player 1 would win if he can enforce the game to stay in some component where it basically cycles in something where the biggest priority that appears is even. Okay, so this is called a parity game. So that's parity games. Now let me give a third example right here. So of mean payoff games. So here we choose for C a finite subset of integers. Okay, so it could actually be real numbers, but usually we just let them be usually integers. And then the mean payoff condition W is the set of pi such that so let's just write lim average of pi is positive. So what do I mean by this? This means eventually in average pi is gonna remain positive. So to be formal, the lim average of pi is defined as the limit when n goes to infinity of the average of the first n terms, so 1 over n sum of the wi. Okay, so the limit of this. Okay, so these are mean payoff games, which also are equivalent to another class of games called energy games, but that's not for this presentation. So again, intuitively here, this means that player 1, in order to win, he wants to remain positive. So this means he should try to trap the token in some component where he can enforce that, in average, the weights that are seen are positive. Okay. So these are the three types of games that we're going to talk about. So first I should mention that these are determined, of course. So determined means that one of the two players, so if we start from a given vertex, one of the two players can ensure a win. Okay, so either player 1 or player 2 can ensure that the game is gonna be winning for himself. So this is determinacy, and also these games are a bit special because they are positionally determined. So this means that the player who wins can also win with what we call a positional or memoryless strategy. So this means that when the token is in some vertex, he can always play the same successor and still win with such a strategy. So these are positionally determined objectives. Okay, so when an objective is positionally determined, well, a strategy is basically just specifying a successor for each vertex, right? So this is a polynomial object, right? So a polynomial object would serve as a certificate of winning. So this means that the game is in NP. And since it is also determined for the other player, this gives that the game is in co-NP, right? So yeah, when I say NP or co-NP, I talk about the problem of determining which player actually wins the game, which is the problem we're interested in. So these problems are in NP and in co-NP, and so far not known to be in P. So this is one of the reasons why, so one of the motivations to study the complexity of solving these games. So it's a problem that is in NP and co-NP and not known to be in P. So there's very few such problems. Okay, so now our point of view is I'm going to describe a tool which is called Universal Graph, which was introduced by Fijalkow and Fijalkow in 2019. And was mainly used to efficiently solve parity games. And our purpose is to see how this can also apply to mean payoff games. Well, actually, the formalism of Fijalkow and Fijalkow was made to solve any positionally determined game, but we're going to see how this instantiates in mean payoff games. And also we're gonna briefly talk about how can one use a universal graph to do a value iteration algorithm.
I will now introduce our basic tool, which is that of universal graphs. So first I need to define graph homomorphism. So let's talk about this first. Graph homomorphism. So I'm gonna say that phi is a homomorphism from G to H if so phi is a function from the vertex set of G to vertices of H such that edges are preserved. So this means such that for each edge E, so let's say from U to V with color C, all right? So an edge of my source graph G. It should be that phi of E, so which is defined as the edge between phi of U with color C and to phi of V. So for each such edge E, it should be that its image belongs to the H set of H. Okay, so this is a graph homomorphism. It doesn't need to be injective, so it could be that, yeah. Okay, now I'm gonna say that a graph U is n universal, so n is some positive parameter. Okay, if two things hold. Well, first, it should be the case that all paths of U, so all infinite paths in the graph, actually belong to W. Okay, our fixed winning condition. Yeah, so we fix a winning condition W. Right, so think parity or mean payoff. So it should be the case that all paths in U satisfy the condition, and also it should be the case that for any graph G which is smaller than n in number of vertices, and such that all paths of G satisfy W, it should be that G maps to U. So this, in this sense, U is universal, so it satisfies W and it embeds any graph which is small and satisfies W. Okay, now why are these useful? Well, there's the once you have a universal graph, you can build a game. So given a game G, you can build the chain product of G into U. So basically G into U means both player plays in G normally according to vertices in for player 1 or for player 2. But then the colors are read into U, and player 1 will move also a token in U according to the color which is read in G. Okay, so it's a game which is played on the product of G and U. Okay, so it's a safety game, and it satisfies that. So given any game G, we can build this game, and it satisfies that. G and this chain product are equivalent. Okay, so G is winning if and only if the safety game is. Okay, this game, as we said, has size of G times size of U, and it's a safety game. So safety games are quite easy to solve. So this can be solved in time. In time and also space, O of the size of the game, so G times U. Okay, so this gives us a procedure to solve game G once we have a universal graph. Build this safety game and then solve it in this complexity. So if we can find a small universal graph U, then we can efficiently solve game of size n. Yeah, so these are equivalent, of course, if size of G is smaller than n. Okay. So let me now give a brief history of universal graphs. So these were introduced by Colcombe and Fijalkow in 2019 in the context of parity game. Parity games. In this context, they were shown by the authors to be equivalent to, so for parity games, to separating automata, so actually to strongly separating automata, if one wants to be precise, which are also equivalent to so-called universal trees. So I'm not gonna really define these, but that's just like for those who know parity games. And actually, so there was this result in 2017 that would give a first quasi-polynomial time algorithm for parity games, a very important result. And then several other algorithms for parity games that work in quasi-polynomial time followed. And actually, all known algorithms, all known quasi-polynomial time algorithms for parity games can actually be seen as, can be formalized as constructions of universal graphs. So our universal graphs, let's say. Okay, so that's an important point. Universal graphs can capture all known quasi-polynomial time algorithms. Also, there's also this nice feature that we have a matching lower bound for universal graphs. So a matching quasi-polynomial time lower bound. So this means that we know that any universal graph actually should have at least this size. So if we want to find a better, for instance, a polynomial time algorithm for parity games, then we should do something which is not captured by a universal graph, right? So this gives us actually a lot of insight as to where to go to find better algorithms. Right, so that's for universal graphs for parity games. Now this raises a question: what about mean payoff games? And actually, what we show in our paper and what we're going to discuss right now is that, well, basically the same story is also true for mean payoff games. I mean that the most efficient algorithms can be captured by universal graphs for mean payoff games. And also we have a matching lower bound. So we know that in order to do better than this complexity, we should do something which is not captured actually by a universal graph. Before going to mean payoff games, I will describe another important part of our paper, which is how to perform value iteration algorithms in a universal graph. So value iteration algorithms are a well-known type of algorithms that was used to historically to solve parity games or mean payoff games, and that have a link to universal graphs, but we formalize it here. Okay, so how can one run a value iteration in a universal graph? Well, first we have to give more structure to the graph, and this is achieved by saturating the graph. So saturate U. Okay, given a universal graph U, saturate it. So this means add some edges to make U linear. So this means that U has some order on the vertices that behaves well with the structure of the graph. Now, once this is done, we may run a value iteration algorithm by so the idea is that we want to construct a mapping, so a homomorphism from our game G to the graph U. So this homomorphism basically represents a winning strategy. And how do we construct it? Well, first we map every vertex, we map everything to the smallest vertex in U, so let's just say U min. And then iteratively, we will somehow, we will resolve some local constraints by changing this map until all local constraints are satisfied, until all are valid. And then once all these constraints are valid, then we may prove that we have converged to a valid strategy and that this is the best possible strategy. Okay, so this gives another way of solving a game when we're given a universal graph. It works in same time complexity. So time is also going to be the order of size of G times size of U. But we have a nice improvement on space complexity, which is now going to be only logarithmic in the size of U. So if we're interested in solving a game with a space-efficient algorithm, then value iteration is a nice solution. Okay, so let me now present the results we have in our paper about constructions of universal graphs for mean payoff games. Universal graphs for mean payoff games. So we let n be the largest weight in absolute value. That is, n is such that the colors are a subset of minus n. Okay, so that's always an important parameter when trying to efficiently solve mean payoff games. So our first theorem, which is actually a very easy construction, gives us a universal graph. There exists n universal graph of size exactly n times n. Okay, so applying our value iteration algorithm, or we obtain a procedure for solving mean payoff games with runtime big O of the size of the game times the size of the universal graph, right? So this matches state-of-the-art algorithms in complexity, and actually it can be seen, so that as an important remark, that value iteration in this universal graph is actually step-by-step exactly the same algorithm as the Brim, Chalupka, Doyen, Gentilini, and Raskin algorithm from 2011. Which is basically state-of-the-art algorithm for solving mean payoff games. So same algorithm as this one. So in some sense, we can capture their algorithm as a value iteration over a universal graph. Now we can slightly, so let's say this is theorem 1 bis, we can slightly enhance this result by giving a construction of a universal graph of size roughly n times n to the 1 minus 1 over n. So this is just slightly better. And then our second theorem is a lower bound, matching lower bound actually, or almost matching, that says that every n universal graph for a mean payoff has size at least an omega of this n to the 1 minus 1 over n. So if we want to go beyond this bound, which we cannot do yet, we need to do something which is not captured by universal graphs or by a value iteration algorithm. So we need to somehow find some really new idea. So that's kind of the conclusion of our paper. There's also a few other results about when we have more assumptions on the set C of weights. We can also find some smaller universal graphs, but that's in the paper. So for more details or questions, please don't hesitate to write to me or to my co-authors. Thank you.